day 2.5 with Kartik's third lecture.
All right. So is this loud enough at the back? Yeah. Okay, so I'm going to start by just recalling the conjecture we ended with last time. So let's recall. Oh, this is terrible. Yeah. It's you press this. No, that's fine.
Yeah.
No, but this is not in the screen. It's out. Okay. There we go. Is that okay? Is that okay? All right. So let's recall the conjecture. So you have a totally real field F, and you have F a Hilbert modular new form. And the conjecture relates the FB, the Peterson inner product, as B varies over all the quaternion algebras that F transfers to. And remember that FB is normalized by requiring it to be rational and even integral as a section of a certain line bundle, okay, on a certain Shimura variety. And the conjecture is that there exists invariance C sub V for V in sigma pi. So pi is the automorphic representation associated to F. Sigma pi is the set of places where pi is discrete series. There exists a set of invariants such that the Peterson inner product equals the adjoint L value, that's 0 pi, divided by the product of the CVs, where V is in sigma B. And sigma B is the set of places where B is ramified. And recall that by Shekel-Langland, sigma B has to be contained in sigma pi, so this makes sense, right? CVs are defined for all such V's. Okay, and the expectation again is that if V is infinite, then the CV should be transcendental. And if V is finite, then CV should be an algebraic integer. And further, these CVs should count level lowering congruences at V, in the sense that if a prime divides CV, then F should be congruent to some G mod P, where V does not divide the level of G, roughly. So V does not divide the level of G. It's a very rough definition, but we'll live with that for now. All right. So in the notes we showed the following. So the notes have the following theorem. Suppose F equals Q, and F corresponds to an isogeny class of elliptic curves. So F is then weight 2 on gamma naught of n. Let's say that F is 2 of gamma naught of n. Then this conjecture is true. So by the way, I should have also said here this is true up to Eisenstein primes. So we'll assume that. An Eisenstein prime is one such that the mod L Galois representation is reducible. So what you want here is, so this should be true up to P units where P is not an Eisenstein prime. Okay. And so in the notes, the following, I've explained a proof of this theorem, and I'll tell you what the CVs are in this case. So what are the CVs? So now first of all, we want to see what is sigma pi. If let's say n was also square free in the notes. If n is square free, then all the finite primes dividing n are in sigma pi. And also there's the infinite place. So this is sigma pi is infinity union the set of all q's such that q divides n. Okay. So C infinity turns out to be the following. You take any elliptic curve in this isogeny class, and you take the Néron differential, so E is any elliptic curve, and let omega sub E be a Néron differential on E, and you take the integral of omega E wedge omega E bar on EC. And C sub Q for Q dividing N should just be the order of the component group of the Néron model of E at Q. Okay. And you might say, well, I chose a curve in this isogeny class. How do the C infinity and CQ depend on this choice? The point is that if P is not an Eisenstein prime, then you can show that these the C infinity and the CQs are well defined up to P units. Okay, and the reason is that if you have another elliptic curve in this isogeny class, so if E prime is another elliptic curve, in the same isogeny class, then you can of course pick an isogeny from E to E prime, and if P is not an Eisenstein prime, then you can pick this isogeny to be of degree prime to P. That's an easy check. And so everything that I've defined over here is going to be well defined up to P units in that case. Okay, so that's the basic idea. Now, in fact, the same proof that I give with some minor modifications there, in fact, goes over to the case where F is just weight 2. So put that here. And I want to show, yeah. So one interesting case to look at is the case of definite quaternion algebras, and that's included over here. I didn't say that B has to be indefinite. So you could look at just the definite case. So suppose B is definite. If B is definite and you stare at what this relation is, it's the adjoint L value divided by C infinity times the product of the CVs where V divides, or CQ, where Q divides the discriminant of B, right? And remember that C infinity is the transcendental parts of C infinity and the adjoint L value are the same. Right? So in these numbers, so if B is definite, the associated Shimura variety X sub B is just a finite set of points. And modular forms of weight 2, for example, are just identified as functions on that finite set of points. So it's clear that you have rationality and even algebraicity. But what this is telling you is that there should be interesting period relations. So there are relations between these F sub B, F sub B's. And this is a case where you can actually compute all of them, because we can work with definite quaternion algebras, right? And we can actually compute them. And one of the goals in of the student projects will be to do this over totally real fields. So student project 1 would be to compute this over for totally definite quaternion algebras over totally real fields. Get this. Let me just say that. But so as preparation for this, Andrew Snowden helped me compute some values over Q, and I want to show you just the kind of values that come up. Sorry? Was there a question?
The traces.
Okay, compute what? So compute No, it was just this. Right.
Between FBB and
The relations between the FBB as B varies, right, over definite quaternion algebra. So I'll show you examples of such relations. Okay. So let's put this on. Oh, I just touched this. Maybe I should put something there. Oh, I don't need that thing. All right. So where do I see this? Right. I can't point. So here's an example. This form. The coefficient field of this form was a number field with that defining polynomial. It's a field of degree 15 over Q. The level was 3 times 7 times 11 times 23. Okay. So if you think of how many definite quaternion algebras you can transfer to, you have to be ramified at infinity, and then you pick an odd set of infinite places where it's ramified. So you see there are 8 choices, right? And we've kind of paired them off. The first is when the discriminant is 3, and the second is when the discriminant is 7 times 11 times 23, and so on. And the reason I paired them off is because what the conjecture says is exactly that if you take these 4 different pairs and multiply the periods that you get on each of them, the product should match up. Okay? So the product of the first 2 should equal the product of the second 2, and so on. Now, you see some very big primes, right? So these are what we have there is the norms down to Q of the Peterson inner products of this form. Okay? And you see there's a very big, what is it, a 13 or 14 digit prime that appears everywhere, and then there's the 838517 that appears everywhere, and then there's this prime 831983, and that appears. It doesn't appear on the first line, but then it appears on the first line of each of the next 3 pairs. Okay? And what that's telling you is that there's a prime above 831983 in that coefficient field that should divide C3. Okay, so the component that should be a component, something like a component group. So you can, and likewise, you can see 241. 241 appears everywhere in the first row, except in the second pair, it appears in the second row. So 241 should divide C7. So this gives you some idea of what these primes look like. So I think this is, so the ABC conjecture, for example, should give you some kind of prediction for how these primes are distributed. It should tell you roughly that the very, very big prime should appear everywhere, and then there should be these intermediate sized primes that kind of move around. Okay, so I just wanted to give an example of these paired relations. You can see that the pairs match up. And in this case, the powers of 2 also match up, and that's somewhat unusual. 2 is often an Eisenstein prime, I think, and so if you compute examples, you will see that the powers of 2 don't always match up. It's just an example to see what the numbers look like. I had no idea what they would till I looked at them. So, all right. So now, put this off. Okay. So what I want to do is change focus a little bit now, and so I should have said that what is involved in the proof of this result, right? So the proof of this result, it's not due to me. I mean, I've just put together stuff that's in the literature. So in the indefinite case, it basically uses work of Ribbett and Takahashi, which relates degrees of modular parameterizations, and that uses Ribbett's very deep work on level lowering. So there's some really deep theorems behind this. And the definite quaternion algebra case also uses something. It uses again what Ribbett did and something similar, but it's all in the notes. So I don't want to go over that. Instead, what I want to do is change focus a little bit and talk about this question from a completely different point of view. See, this worked in weight 2 over Q, right? And we'd like to generalize this to other contexts. So for example, we'd like to generalize this to higher weight. And we'd also like to generalize this to totally real fields. And these kind of geometric arguments get more difficult or even impossible. For example, in higher weight, you can't give the same geometric arguments that you give in weight 2. So I'm going to change focus and come at the same problem from a completely different point of view, namely the theta correspondence. So instead of this kind of more geometric way of looking at it, we'll look at it from a more automorphic point of view. So I'm going to just recall the main constructions in the theta correspondence. Okay. So we'll put ourselves in the following situation. We'll say that, let's say F is a number field, any number field. Okay. I'll write AF for the dels of F, and we'll let W, bold W, a symplectic space over F. Okay. So what this means is there is a form, a bilinear form, W to F, that is non-degenerate and alternating. Or skew symmetric, I guess it's the same thing. Okay, and we'll fix psi, an additive character of AF mod F. So the constructions that I'll be talking about depend very much on this choice of psi. Okay. Now it turns out that one can construct, so let S be W, a symplectic group of W. So SPW is just the group of linear automorphisms of W that preserve this symplectic form. For later use, I'll also need maybe GSPW, and GSPW will be the same thing except that this is the similitude group. So these are linear automorphisms that preserve the symplectic form up to scaling. I won't write that. And it turns out the key construction is the following, that if you take the symplectic group, SPW, and take its adelic points, then one can construct a certain cover of this group called the metaplectic group. I'm going to call that MPW of A, and we're going to write A instead of AF for simplicity. And this is a C star cover of this group. Okay. The notation here is a bit misleading. The point is this MPW is not an algebraic group, so it's still customary to write MPWA. Okay. It's a non-trivial C star cover of SPWA, and I should put a psi there because the construction of this metaplectic group depends on the choice of additive character psi. And it turns out that this metaplectic group has attached to it a certain representation called the Way representation. Call it omega sub psi. So this is a representation of MPWA into the automorphism of some space, and I don't want to get into what that space is and so on. But the important thing is that there is an interesting representation called the Way representation, and this was constructed by Way in a classical paper in the 60s. And the point is the reason this is interesting is you can often find examples of two groups, G1 and G2, inside NPW. I'll give the exact definition, something called a dual reductive pair. And you can use this representation, which is a rather small representation of the metaplectic group, to transfer forms from one group to another group. Okay? So let me also give the key definition here, namely that of a dual reductive pair. This notion is due to Howe. So this is a pair, G1, G2, of reductive groups. So G1 cross G2 sits inside SPW. Okay? And G1 and G2 are centralizers of each other. Okay, I'll give some examples in just a minute. Now, why is this interesting? As I said, what you can do is the following. You have G1 cross G2 in SPW. And so I guess I should have written that better. So you have G1A cross G2A sitting inside SPWA. And then you have this cover, which I've called MP psi WA. So you can look at the pre-images, which I'll call G1 tilde A, or G1 A tilde, and G2 A tilde, sit inside there. And this group has the wave representation. So what you can do is use this wave representation to produce a kind of integrating kernel to move forms over or functions over from G1 tilde to G2 tilde. Okay? So this is the basic construction that's going to come up. Now, in the cases of interest to us, it will turn out that the metaplectic cover, which is not split, right? This extension is not split, but it will turn out it will split over G1A and G2A in the cases of interest to us. So not just can you transfer functions between the tildes, but in fact you can use this to transfer functions or forms from G1A to G2A and backwards and in the other direction. Okay. All right, so let me give an example, or two examples in fact. So the first example is the following: let W be a symplectic space and V an orthogonal space all over F. So orthogonal just means that the bilinear form is symmetric as opposed to skew symmetric. Okay? And let's take boldface W to be the tensor product of these two. Right? Now if your tensor is symplectic space and orthogonal space, you get a new form on the tensor product, just taking the tensor product of the two forms. And because one of them is skew symmetric and the other is symmetric, the tensor product of the two forms is going to be skew symmetric. Okay? So W is a symplectic space then. Okay? So I can take the symplectic group of W, and I can take the orthogonal group of V. So this is just the linear automorphisms of V that preserve the bilinear form in V. And this is dual reductive. It's a dual reductive pair in SPW, SP boldface W. So that's the first example, and I'll say a little bit more about this in a bit when we come to the Jacques-Langlands correspondence. Here's another example. Let's say that E over F is a K over F is a quadratic extension. Okay. And suppose that V1 and V2 are unitary spaces over K. So what this means is that they're vector spaces over K, and so they're equipped with, so V1 is a K vector space. Equipped with a form from V1 cross V1 to K. And to say it's unitary, so there's a non-trivial involution here, which I'll call, I guess I'll just write that as bar. Okay, and so this form should satisfy alpha x beta y equals alpha bar xy beta. And I'll want V1 to be Hermitian and V2 to be skew Hermitian. So for V1, what I want is that if I take xy, this equals yx bar. But for V2, everything would be the same, except that you would want xy to be minus yx bar. Now, so what is the dual reductive pair in this case? So I can take the following space. I let W be V1 tensor V2 over K thought of as an F space. As an F vector space. And I make a form on W by doing the following. I take the tensor product of the two forms on V1 and V2 and take the, so this gives me something in K, and then take the trace down from K to F of this form. Okay. Now because I picked again one of these to be Hermitian and the other to be skew Hermitian, the resulting form is going to be skew symmetric. Okay. This will be skew symmetric. And now you can look at the following pair. You can take the unitary group of V1, the unitary group of V2. So these are just linear automorphisms that preserve the form on these two groups. This is contained inside the symplectic group of W, and this is a dual reductive pair also. Both these pairs will play a role in what I'm going to talk about. Okay, so now, as I said, you can use the wave representation to transfer forms between G1 and G2, or G1A and G2A. And the explicit way to do this is to construct a theta kernel. So we can use the wave representation to construct an integrating kernel. This integrating kernel will depend on certain choice, and the choice will exactly be some phi in this S, where S is the space on which the wave representation acts. Okay? I'm not going to say exactly what that space is. It's a certain Schwartz space, but we won't go into that. So associated to such a phi, you can make a theta function, which I'll call theta sub phi. And so if you have these two groups, G1 and G2, a dual reductive pair inside SPW, you have a form, say F1 on G1A, then you can define the theta lift, theta sub phi of F1 as the integral of, I'll just call this, as the integral of F1 of G1. And so this is going to be some integrating kernel on the on SPW, but in fact on the metaplectic cover, but I can restrict this to G1A cross G2A sitting inside there. Okay. So the point is you have some function on the first group, and you have some integrating kernel, which is a function of two variables, G1 and G2, and you integrate this form F1 against this kind of integrating kernel, which is these two variables, and in the end you end up with a function on G2. So this is a function on G2. Okay. And likewise, you can go in the opposite direction. So I won't write that down. Okay. And the interesting thing is that even though the wave representation itself is a very small representation of the big metaplectic group, when you restrict it to these products, it gives you interesting representations, and you can move interesting representations back and forth. Okay. So the first example of this, before I do that, let me just say this. If pi, maybe I'll just give this example directly. And the first example is, this is the Shimizu correspondence. So this is the explicit form of Jacquet-Langlands. And the point is here, you take V to be, so let's say V is a quaternion algebra over F. You take V to be B, okay? And the bilinear form is just going to be xy equals xyi plus yxi, where I is the main involution. And you take W to be just a two-dimensional symplectic space. So recall that SPW OV is a dual reductive pair. But SPW is just, in fact, as I said, often you want to work not just with the symplectic or orthogonal groups, but with the similitude groups. So in fact, I'll want to look at GSPW and GOV. And so the G's just stand for linear automorphisms that preserve these forms up to scaling. Okay? So what is GSPW? Well, since W is just two-dimensional, this is just going to be GL2. And what is GOV? Well, it turns out that you can make a map from B cross cross B cross to GOV as follows. You take a pair alpha comma beta, so take two elements in B cross, and you send this to the map that sends an element X in B to alpha X beta inverse. And then it's easy to check that this preserves this form. That's a simple check. And where it lands is in fact in the connected component of this group. Now, what's the kernel of this map? The kernel of this map is exactly going to be an F cross embedded diagonally in there, as you can see. If you take an F cross and embed it diagonally, then clearly it's going to go to the trivial guy. Okay. So the theta correspondence now provides you a way to lift automorphic forms from the group GL2 to this group, which is B cross cross B cross mod F cross. Okay. Now, what should forms on this second group look like, right? Because there's the diagonal F cross embedded inside there, so forms in this group look like, write that here. So forms on B1 cross cross B2 cross or F cross look like pairs pi 1 comma pi 2, where pi 1 is a representation of B1 and pi 2 is a representation of B2, such that the central characters, which I'll call say omega pi 1 and omega pi 2, these are the central characters. The product of these central characters should be trivial. Okay? That's the kind of condition that one would get. Now, in fact, one can realize explicitly the Jacquet-Langlands correspondence in this way. Namely, you start with a pi which is on GL2A, and you ask, what do I get by taking the theta lift of pi? And the answer that Shimizu gave is the following. Well, theta lift of pi is 0 if pi doesn't transfer to B or to B cross. Okay, and if it does transfer, then what it is pi B cross pi B dual, where pi B is the Jacquet-Langlands transfer of pi. Okay, so remember that not everything on GL2 transfers to a given quaternion algebra. Right? There's a condition that Jacquet-Langlands give, namely that the quaternion algebra can only be ramified at those places where your representation is discrete series. Okay? And this provides a very explicit way, the theta correspondence provides a very explicit way to go back and forth. And it tells you exactly that, well, you get 0 if you don't transfer, and if you do transfer, then you get the representation you expect across its dual. Okay? Now, in the case we're looking at, so in our case, because we're always looking at gamma 0 level structure, so our central characters are trivial. And so this implies that in our case, we'll always have the dual is isomorphic to itself. So we can think of this as going to pi b cross pi b. Okay. Now that's not enough. This is just a purely representation theoretic statement, right? If you want to compare periods, you want to say something about explicit forms in these representation spaces. So that's something one would like to do. We would like to explicitly study. So pick some f in pi, right? That's what we've been doing, and compute explicitly what theta phi of f is, and what you'd like to get, or what you would get, is some scalar times fp cross fp. Okay. All right. So the point is, first one needs to check that one can write down a phi such that this is the case, okay, up to a scalar, and this can be done. So can pick phi to make this happen. So f and fp are these normalized forms that I picked, right? But now everything goes into, all the interesting stuff is happening in the scalar that you pick up over there, right? From the representation theory point of view, you know exactly what's happening, but from an arithmetic point of view, you started with something that is arithmetically normalized, and you made some explicit lift, and you want to know what multiple of this arithmetically normalized form do you get, okay? All right, so how do we study this? So remember, we're looking at the lift from GL2 to B cross B cross mod F cross. But it turns out, of course, that this is a lift in the opposite direction. Right? And well, that will send FB cross FP to some multiple which I'll call beta of F. Now, the lift in the opposite direction is easier to study. So this lift is easier to study. And the reason this is easier to study, as you might guess, is GL2 admits Q expansions or the Whittaker models. So you can compute explicitly, since you can compute explicitly with Fourier coefficients. On the left. Okay. So at this point, I should tell you, I should introduce another notion, which is that of a seesaw pair. So maybe I'll put that here and introduce this. Is that better? Okay. So there's a very important notion, that of a seesaw dual reductive pair. This is due to Kudla. It's a very simple definition, and it's just following. If I have a symplectic space W, then two dual reductive pairs, G1, G2, and H1, H2. These are dual reductive inside SPW. Then these form a seesaw. I'm sure you can already imagine what this is going to look like if you have a picture like this. This is how it's denoted. Right. Why is this interesting? Right? Why is this an interesting definition? The point is, you can start with, suppose I start with the form F1 on H1, okay, and a form which I'll call, say, F2 on G2. Now, and I pick some choice of theta function. Now I can make a theta lift here and go to H2 because that's a dual reductive pair. Likewise, I can make a theta lift there and go to G theta phi of F2, and that will live on G1, right? Now I can restrict these forms and integrate. So I can integrate F1 against the restriction of theta phi of F2 to H1. On the other hand, I can take the lift in the opposite direction, theta phi of F1, restrict that to G2 and integrate against F2, right? And it's by a simple change of variables, one can show that these two are equal. So anytime you put yourself in a situation where you have dual reductive pairs, you immediately get relations between various kinds of integrals. It's a very simple consequence of that. So of course, this is useful only if you have lots of examples of of seesaw pairs. So let me give you an example of a seesaw pair. So remember that if we have V orthogonal and W symplectic, then O phi SPW is dual reductive inside SP of boldface W, where boldface W is just V tensor W. And let's say that V splits as the direct sum of two orthogonal spaces. Okay. Well, now you can see you have following kind of dual reductive pair. You start with OV SPW. Okay. And inside OV, you have OV1 cross OV2. Because this is an orthogonal decomposition, the orthogonal groups of the two subspaces V1 and V2 embed inside OV. And that will. So you get two pairs of dual reductive pairs, SPW cross SPW, OV1 cross OV2, and SPW OV, and the SPW is embedded diagonally inside there. Okay. In fact, this applies immediately to our situation. So maybe I'll switch. Come back over here, right? Okay. So let's apply this idea to the situation that we have over here. So the first thing I said is that, so remember this is of this form GSP, W, and OV, right? The first thing I said is that it's easy to compute the lift in this direction because you have Fourier coefficients. So what one can show by this computation, you can show explicitly what beta is. That beta is in fact equal to the inner product of FP with itself. Okay? That sounds reasonable, right? Because I've normalized this F such that its first Fourier coefficient is 1, and what I pick up there is exactly the Peterson inner product. And so now I can use this this identity, which is called seesaw duality, to figure out what alpha is. Okay? So what's alpha going to be? Well, alpha, okay, let's just write this. So alpha times FP cross FP against FP cross FP is just beta times FF. Okay. And beta was FP FP. And so here you get an FP FP squared, and so what you get is alpha is FF over FP FP. Okay, so you notice what's happened. This is the kind of thing we were interested in studying, this kind of Peterson inner product. And what's happened is we constructed this explicit theta lift, and the coefficient that came up over here is exactly the ratio that we're interested in studying. So what you want to understand is what can we say about this alpha? Can we say something else about this alpha in a completely different way that will therefore tell us what this ratio is? Okay, so that's what I'll talk about next. Okay, so here we have this picture. We have GL2, which is GOV, okay, and we have this F, which lifts to some alpha times FP cross FP. And we want to understand what this alpha is. Okay. Now, let's put ourselves in just the following situation. Let's say that our field F is Q. Okay. So in fact, I should have said this before. All this is true. The Shimizu thing I was talking about explicitly is just when F is Q for now. So let's say F is Q, and let's say B is indefinite. Okay. And I want to understand what alpha is. Now, I can think of this form as a form on, let's say I have just a form on B cross. Remember that I can think of this as a section of a line bundle on the Shimura curve X sub B. And you want some criterion to check if this section is rational or even integral, right? So how might you check if a section is integral? The point is that you can think of, if you think of usual modular forms, the usual modular forms are not just functions in the upper half plane, but they're functions in the upper half plane satisfying some transformation, right? So you can think of them, if you think of modular curves as moduli of elliptic curves, then you can think of modular forms as functions not in elliptic curves, but in a pair consisting of an elliptic curve and a differential, right? That's how one thinks of it. So usual modular forms are functions on pairs consisting of an elliptic curve and a differential. And likewise, in this case, this curve X sub B is also a coarse moduli space. But now for abelian surfaces with B action, with endomorphisms by B. Okay, and the same way you can think of modular forms on such curves as functions now on abelian surfaces with appropriate differential. Okay, and so in the setting you can ask, well, what does it mean for a section to be rational or even integral? Okay, and what it means is that if you evaluate your as in the case of usual modular forms, if you evaluate this modular form on something that's on something that has good reduction at p, for example, or something that's say rational, and you take a rational differential, it should be rational. Or if you want to do integrality, if you evaluate in something that has good reduction at p, and you pick a differential that's a unit that's integral and a unit at p, then what you should get is integral, right? Now, it would be hard to check this for all pairs, but instead, you might try to check it for something like a dense set of points. And a nice set of points to check is CM points. So you can check this on CM points. Okay. Now, if you look at the advantage of CM points is we can actually do something. We can go back to the theta correspondence and do something with them. So how do you get a CM point? A CM point comes from picking an imaginary quadratic field and an embedding of this imaginary quadratic field in B. And if you recall what I told you about the canonical model, for example, right, these points are certainly algebraic. These give you algebraic points on the Shimura curve. But the point is that the corresponding abelian surfaces, in fact, have good reduction because they are just products of CM elliptic curves. So what you'd like to do is, okay, I have a form F now on B cross. I have K cross sitting inside B cross. And let's say I have a form, which I'll call, say, G on B cross, and I want to figure out what its values are at CM points corresponding to K cross. And so the idea is you want to compute some kind of integral of G restricted to the idels of K. Okay? This doesn't quite make sense because at infinity this is the wrong type. So to make sense of this, you need to pick a Hecke character of K. Of the right infinity type. And so the infinity type here will have to be something like 2, 0 of infinity type 2, 0. And this 2 comes from the weight of the form. Okay. So all I'm saying is if you take a form of weight 2, think of it as a form on the idels of B cross and restrict it to this embedded K cross and integrate against chi. This gives you something that's well defined. Okay. I'm going to call this L sub chi of G. Okay. And what this is really is a finite sum of values of G twisted by this Hecke character. Okay. All right. So, and so the criterion is going to be roughly the following: that G is rational, respectively integral, if these kind of periods that you compute are rational or integral up to what? Well, you're choosing a CM point, which means you've chosen either a CM elliptic curve or a product of CM elliptic curves and some kind of differential, right, on this thing. So the periods of that differential are going to intervene in this definition. So up to periods of CM elliptic curves. I'll just call this CM periods. Okay. All right. Now, how can we apply this? So, all right. So, yes. Yeah. No, you can take right. Well, if you can vary the CM elliptic curve, for example, you can vary this field, for example. Right. Sure. For the rationality. For the rationality, sure. The rationality is a little delicate to state in terms of, right, you want to say something about the Gall action and so on. For the integrality, you don't care so much when you talk about the integrality question, right? Right. Well, you take a CM elliptic curve that is good reduction at P, take a differential that is a unit at P, and take a period of that differential. Yeah. So yeah, you can in fact check this numerically. It's in some of this is in the notes. I've given examples, explicit examples of this in the notes. Right. So if you go back to what we were doing, we wanted to compute this kind of we had that kind of lift there, and we want to compute what this alpha is, right? So I'll rewrite this here because you can't see it there. So roughly speaking, the point is that you have this GL2, which is GSP of some W, and then you have GOV, which is B cross cross B cross, or F cross, and you have this form F here, which goes to some alpha times FP cross FP. Okay? So what you want to do is restrict this to an embedded K cross cross K cross mod F cross, and integrate against a product of two chi's, right, roughly. Now, remember that you have this kind of dual, if you can write, so I have K sitting inside B, and I can decompose my B, which is V, as a sum of K plus an orthogonal complement, right? So I'll call this V1, and I'll call this V2. And now I have a kind of dual reductive pair, where I have OV1 cross OV2, and here I have two copies of GL2. Okay. So there should be G's here, and I'm kind of fudging some things, but that's, the picture is roughly correct. Right. And the map, you have to keep track of what this map is also. So if you keep track of what this map is, then roughly speaking, what you want to do is you have this lift, you want to restrict it and integrate against chi cross chi, but instead you can lift chi cross chi to the other side and then restrict and integrate to F. Now if you keep track of what the map is over here, the map turns out to be x comma y goes to xy inverse, xy bar inverse. Okay. So when you work this whole thing out, it turns out that you get alpha times the integral of fp cross fp against chi cross chi is the integral. So the chi cross chi, because of this, the change under this map, it goes to, it's the lift of chi cross 1. Just to work that out. And this is on GL2 cross GL2, but now you restrict this to GL2 and integrate against F. So what you get on the, in the end is something like F times the theta function associated to chi times the theta function associated to the trivial character. Okay. And again, you have to be careful with all these things, and it turns out that one of these is, this is, in fact, what you get is a kind of usual, the bar of the usual theta function associated to chi. So you can write this as some kind of inner product, this form. Now there are various ways to proceed. You see, on the left you have alpha times L chi of fp squared. Okay. And what you can do is you can pick the CM point such that this guy is in fact a unit, mod CM periods. So I divide by some CM period, and on this side I divide by a CM period. Now it turns out that this theta sub 1 is in fact an Eisenstein series. And what you get here is exactly the, in fact this is a value of an Eisenstein series rather, of an Eisenstein series, which I'll call E sub S. And the value, this turns out to be exactly the value at the center, which I'll call sub half, of the same thing where I replace F by this Eisenstein series. Okay. Now this is in fact the integral representation for a certain Rankin-Selberg L function. And the Rankin-Selberg L function is the L function LSF chi, where this is, you either take the base change of F to, so maybe I'll write, I should call it LSFK chi. So I'm almost done. Right. And now the idea is that you can show, so this idea is due to Harris and Kudla originally. So Harris and Kudla basically show that this L value divided by the CM period is rational. And so once you know the rationality there, then you know that alpha is rational. Okay. Now, if you want to prove integrality results, then you need to show that these L values are in fact integral. So in fact, so this is something that I did a few years ago. In fact, the L values are integral. And as you might imagine, checking integrality is a fair bit more delicate. In fact, this proof used the main conjecture. So this is, which is not a conjecture, use the main conjecture for imaginary quadratic fields. This is the Iwasawa main conjecture. This is a theorem of Carl Rubin. So it's, though I said conjecture, it's in fact a theorem. Okay. So the point is you can use this theta thing to convert checking the integrality of alpha to the integrality of an L value, and that you can check using some Iwasawa theory. Okay. Now, what this tells you is that this alpha is integral, right? And of course, you'd like more than that because what you expect is alpha is a product of some of these CPs, right? And so, can one actually get the factorization? So this is not done as yet, but I expect that one could use, for example, p-adic families to get something like this. So I'm not going to talk more about this, but in the next time, I want to kind of move to the totally real case and explain how some of these ideas can be generalized there. This method doesn't itself give you anything much because these ratios FF over FP are not expected to be, for example, algebraic, even if B is, except when B is totally indefinite. Okay. So just the Shimizu correspondence itself won't work, but we can use other theta correspondences, and I'll talk about that next time.